Okay, so how was the exam? How did it go? Too easy, too short, too long? Too long. But it wasn't hard, right? Okay. Can you read this? It's not quite readable, right? So I'm gonna try to. Okay, so most of the problems were very self-descriptive. So if you were attentive to the text, you would get a hang on to the solution. That the text would guide you to the solution. It's also apparent in the first problem. The first problem tells you that we sample from the data we have, then look at the averages of our predictions. Then we compare what does the averages of predictions do compared to the, rather than having just one prediction. So on one hand we have F, on the other hand we have m different samples from D, and we look at the averages of m different predictions. So these are identical samples, and they also have the same size. So they have the same statistical properties. All Fi's in this question have the same statistical properties. Then clearly, right, expectation of the average of something is just the expectation of the individual thing. In this case, the average is f hat, and the individual thing is just one of the f's. And we get by this equality here that the expected value of z bar is z, expected value of z. Why? Because the expectation is linear. Any questions? Part 2. What about bias? Bias is just the difference between the expected value of our predictions to the true value. So it seems like it's a linear quantity. Looking at the bias of z and bias of z bar, we see that they're equal because of part 1. Their expected values are equal, and mu is the true value, which doesn't change depending on the side, which side of the equation you are. So you get the same value. Just most questions have simple one-liner answers. The third part asks about the variance. Now in this case, variance is not a linear operator. That part can be a little tricky, but all the information that's needed is given in the question. What breaks linearity is the first equation here in the hint, that if you multiply a random variable with a constant, then its variance scales with that constant square. Right? Then using that, taking that 1 over m out gives you 1 over m squared times the variance of the sum. Now you can break the sum apart using the second equation given in the hint, which gives you m times variance of one of the random variables. And remember, in the denominator we had 1 over m squared, so one of the m's cancel, it gives you variance of z divided by m. Fourth part, which one would you choose? The one that has a lower variance is a better candidate to choose. If you are the one who gets to choose. And part 6 is just a description of random forest in a few lines would do. Oh, I skipped part 5, sorry. So in part 5, since the reasoning, the general reasoning, the common sense reasoning is that you choose the one that has the lower variance. In part 5, what this equation tells you is that if you have correlations, you tend to have higher variance. So you want to use the one that has less correlations, right? Because you want to use the one that has less variance, the smaller variance.
And was just
that's enough. Yeah. Yeah. And just because you would use the one that has less variance is enough of an answer. Classification trees. Remember, we had this simple tree. And the thing we want, so I saw some papers that got confused in this question on what to look at. You know, in first part, I saw some answers that somehow separated the data that has 4 items into, you know, path, distance, and open space. But what is asked is really, you know, the main thing is whether the place is desired or not. So it's like a coin toss that in which you have 4 coins, and the outcome is either heads or tails. In this case, outcome is whether the place is desirable or not. And then you have certain other properties, like the coin is biased, or the coin is like a dime or a quarter. You look at other properties. That the main thing is whether it's desired or not. So each PI here, it should actually refer to the probability that the place is desired or not, right? So given the sample, you have 4 elements in the sample. What's the probability that a given place is desired? It's 1/2. There are 2 possible outcomes, right? It's yes or no. So it's like a binary problem. So what you would have is the sum of 2 things. Look at the first term is the yes term, let's say the second term is the no term. Then each PI is 1/2, because judging by the data you extract that probability information, then you get 1, right? Because log 1/2 in base 2 is 1 also.
What do you mean there when you give the formula of entropy? You say that it's on a set of size n.
A discrete, so it's like, I mean, in the same case, probability of a coin is heads or tails, right? So it's your omega is h or t. That's what it refers to, and the size of omega here is 2. So if I was looking at 2 coin tosses,
would be the size of the set of the target variable.
yes. So it's like your event is the coin toss event. You can flip as many coins as you like. The outcome will be heads or tails, your sample space, right? Because you are tossing it once. You don't do it twice. So you know, tossing 2 coins in a row would mean buying 2 apartments, right? 2 apartments in a row. You don't do that. And your sample space is this, and then you draw samples from that.
I think that many of us got confused with the
that was great.
because size of a set of size n.
Sorry. It's back. Okay.
At least I thought that it was how many observations you had in your test.
Yeah, but that's, you know, in a sense, that's testing a basic probability knowledge, right? So what if I've given you results of 5 coin tosses? How would you do? Then your n is 5? No, it's not, because your sample space is given. The size of the sample space is known. You have it at hand. So it's you know, coming up with the probability model of the problem.
No, I understand that, but it's just a little bit confusing how it's written.
Well, I think the description of the problem is pretty clear, because it emphasizes that you should focus on the desired column, right? And the desired column has 2 elements. It's either yes or no. There's nothing else in it. Yes?
I guess it was because on the homework, they define it like n as the number of elements that you have in the node.
Yeah, here it's the same thing. There's the yes node and there's a no node, right?
So in the yes, number of elements in the yes,
Yeah.
there are 2. So how we do it is number of yes, the total number of elements in the node.
But it doesn't. It gives you the wrong answer.
Yeah, but that is what was expected in the
No, not according to the solutions. It doesn't give you the correct interpretation, right?
Yeah, but like this was the thing that was expected according to the assignment.
Mhm.
When you have three nodes,
Uh-huh.
number of nodes which have the label yes upon the total number of nodes, upon the total number of nodes, this node with the leaf.
Yeah, but that's confusing two things. The first part, actually, in this, when you read it, there's no separation between leaves, right? You only have a set, and you have 4 samples. So in this problem, before even starting to separate the data, you start your parent node. In the parent node, there's no separation. Then you focus on the parent node, and you need to come up with the entropy of the parent node. Now you didn't even split the data, right? And then the parent node, you have 4 samples, and from that 4 samples you gather probabilities because you don't know the actual probability distribution because those 4 are the only ones that you've seen. That's why the first part wants you to focus on the desiredness because that's your main thing, and then looking at the features, you'll separate. Then comes the leaves. So there will be 3 different ways of separating the data. Each one looking at the different features, right? The features, so the text of the question somehow forces you to understand that desired is not the feature. Desired is what we are looking at the end, right? The features that we are gonna use to separate are pets, distance, and open space. Yeah, so that's why the two parts, it's maybe, it should be a hint that the first part is like the introduction, and the second part has 3 subparts within itself that forces you to deal with the problem itself. Because so even if you did the first part the way some of you did, then how would you continue in the second part? The second part asks you to calculate the parent entropy minus weighted average of the children entropy. How are you going to come up with the weights? What's the weight then? If you start the separation by looking at the desirability, how are you going to calculate W1 and W2? Right? It makes everything unclear. Right? But it's not unclear. So you could somehow reverse engineer the problem to fix the first one. I mean, don't get me wrong, more than half of you got the problem correct. But the ones who didn't get it right,
What was the
it's
confusion with those who did it incorrectly?
focusing on the individual example gives you like probability is like 1/4 times log 1/4, and there are 4 terms. But many people also got partial credits for that too, so it's not a big loss. But I want you to understand the main issue here. The third part, for part C in 2, you didn't have to do any calculations. It would be enough. So some of you, you also got credits if you did a wrong calculation in the first one, but if the same carries out in the other parts, you get full credit for that because you don't want to be punished multiple times for the single mistake. So part, even if you did part A and B wrong, in part C you said it's somewhere between A and B, you get full credit for that part. Because the point is that it's gonna carry less information than one feature and more information than the other feature. So its information gain should be somewhere between the two. You didn't have to go through the calculation. And part 3 is just an obvious result from the, looking at the 3 numbers. Again, you could get the numbers wrong, but the interpretation correct, and you get full credit. The third problem part one is just obvious.
Actually, if then when you continue reading and you see that it is possible that the prediction is a zero in the algorithm.
No, here it's given you that it's from RD
Yeah, but
cross
then
minus
there's
1 to
a
1.
verification that g of x can predict zero. There. May also produce
Which
a
one?
zero
Which
value
line?
In the 3. G of x
Here.
may also produce a zero value if there is no preference between there.
Here.
That's the sign.
The,
Sign of
the,
secrecy.
the parentheses.
But G is the return of the averaged one. In part one, it asks you what the base classifier returns. Base classifier is just GM,
Okay.
right? So it's a little, once it's not a presentation, it's a little hard to navigate. So look, the base classifier is this one. There's a typo here. So this GM is not GM, of course, it's indicator function of GM xi not equal to yi. Right? So it's the 0, 1 risk. It's in the slides of the corresponding section. The other boost is just the linear combination of the predictions. Alphas are calculated on the way with the algorithm. Then at the end, you just take the sign of it. It's also just the usual thing. If you did the homework or if you read the slides, you probably would have remembered it. I think most of you got it right. The part 4, of course you did it, but it's hard to remember, so the description is given in the text. And the key there is the optimization part, right? H and V are chosen to minimize the empirical risk. So you just choose H and V, you just write the loss function and find argmin of the two of them together. That was also part of the homework. One part of the homework, the optional part of the homework, even if you didn't solve it, the text of the homework was telling you that, the title of the homework was that if you use the exponential function in FSAM, it gives you the other boost. They correspond to each other, so you just write the exponential loss, then you're good to go. Part 6. Is it true or false? What did you think? Huh? Yeah, but I mean, now you see it, but what did you think in the exam? And it's false because their hypothesis space is different. Right, one has a hypothesis space parameterized by V, then it's V times X, V transpose times X. Then the other is just, it's combinations of this that gives you, that's the larger space. So it's not easy to recover. The 7th part is just an estimation problem. There is a typo that we fixed during the exam. I hope it wasn't frustrating. So the typo carries over here, it's not fixed here. The point is not the fact that gamma m is less than 0.5. The whole point is that gamma m is away from 0 and strictly away from 0. So gamma m has to be strictly away from 0. So there's a gap. And why do we need the gap? First of all, if I have a product, how can I have that product go to 0, I have to have its terms to be less than 1, right? But I have to have its terms to be strictly less than 1. Because if I have this product of AM where m from 1 to infinity, then if I know that AM converges to 1, I can't guarantee convergence of this product to 0, right? That's why I need gamma to be strictly away from 0. So the first point you needed to write was the fact that this square root is less than 1, but it's strictly less than 1 because it's strictly less than 1 minus 4 times gamma squared, so that it doesn't converge to 1. And the second point is to notice that the range of values that the function can take is discrete. It can be 0, 1 over n, 2 over n. So as soon as it's less than 1 over n, which will happen because it converges, you just established the fact that it converges to 0, then it will be 0. It will reach 0, and it will reach 0 in finite time. Yes?
I have one doubt. If gamma is 0, for example,
Yes.
it's less than a half,
Yes.
and you have a multiplication of a lot of ones,
Yes.
and never wanna be reached 0,
Yes, true.
and
Then it doesn't work. That's why gamma has to be away from 0. This is a fixed number that's away from 0. Maybe you're confused with the type of this. This is fixed, so this is not. So this first line, suppose we have gamma m less than gamma less than 0.5, is no longer the case. The correct version is, suppose we have 0 less than gamma m. That less than 1/2 actually. Yeah.
Could you explain why you can improve on the test performance after you have 0 error on the train? That's not a problem, but we went over it. I just didn't get it.
I mean, it doesn't guarantee, right? It doesn't guarantee anything about the test. Does it?
that typically happen?
That's a generalization problem. The generalization problem in machine learning in general refers to whether finding a minimum in training set gives you a minimum in the test set. Sometimes it doesn't. We know it doesn't because there's a phenomenon called overfitting, right? Sometimes you find lower points, it gives you a higher error. You maybe shouldn't have done that. Maybe you should have controlled your test set or validation set before it starts to increase, right? You remember the typical plot of training curve going like this and the test curve going up like that somewhere. That's the generalization problem, and generalization problem has different effects on different problems.
I thought adaptation was one of, maybe I'm confusing.
it doesn't increases in the right part, but it doesn't go to 0.
This can go to 0. This is the.
So I don't understand the mechanism that allows you to improve once you've got 0 error.
Well, once you get 0 error in the training set, you memorize data.
I remember, maybe I'm remembering incorrectly, but I thought I remembered that there were cases where you could continue improving even though you perfectly labeled your training.
Oh yeah, you can. Yeah, so
You can, there's no guarantee.
you can separate the data perfectly, but depending on the loss, your loss can still decrease, right? So that's different because I think you're asking, suppose you have this data, this separates the data perfectly, right? But depending on your loss, this function will have a lower loss value. So the fact that you separated the data doesn't mean that you found the lowest possible training cost. Your training cost is still parameterized and depends on where you put the exact line. And it probably has some sort of landscape like this in the parameter domain. And its values will be the loss values. Maybe this separates your data, but maybe finding another local minimum here will give you a lower loss. And that might have better generalization or that might have worse generalization, depending on your data. Does that clarify your previous question? Okay. So the part 8 of it is that, of course, if you have the situation in which you have the same x but different y's, then what's going to happen is that you won't have this non-convergence to 1, right? You guaranteed that the factors didn't converge to 1, but now it's not the case anymore. So the assumption of the previous part fails, hence the result also hold true. Yeah.
Sorry to ask again. You said in the exercise that you reach 0 infinitely many steps.
Yes.
But m has to go to infinity to go to 0, right?
True. Right.
So it's infinite, not finite.
Yes. Why does it converge? So many people didn't get that right. It's good to emphasize.
Yeah,
So why does it go infinite? Even if we need m to go to infinity in order to that function to go to 0. What's the possible values of that function? We are looking at the empirical risk, right?
Yes.
And empirical risk is discrete. It can be 0, 1 over n, 2 over n, all the way up to 1. So I know that since it goes to 0 as m goes to infinity, I know that there is a finite m, let's say capital M, that's large enough. I don't know how large, but it's large enough so that at some point it's going to be some positive number between 0 and 1 over n.
Okay.
Right?
Yes.
Once that happens, once I prove that the empirical loss is less than some number that's between 0 and 1 over n, what can it be? It has to be 0. It has to be exactly equal to 0 because it doesn't take any other values. Its range is limited. Right? The range of values that that function can take, the function I'm trying to bound. If I show that it's less than this, then there are 3 possible values. This is 0, this is 1 over n. I'm telling you that there's some m, some capital M that's high enough that that function will be less than some point here. And if it's less than some point here, it can be anything in between. It can't be that as well. It can be that point too. It has to be 0. And that capital M is the finite number that you are looking for. In the multi-class classification, we have to form the function psi. Psi is x cross y. X is in R2. Our samples are drawn in R2. And y is the set that has only 3 elements, 1, 2, 3. So, and of course, RD is going to be, the D is going to be 6 in this case. And it's just a simple representation of psi. And you know, this f is just rewriting of what's here. So this part would be enough. In the second part, the delta function is given in the table. And we just have to put things in place and do the calculation. So you can take the I to be 1 here, or 1s to be I, it doesn't matter. It's just the H, the outputs of H is for the sample X we have in hand. So if you call it X1, then we can calculate the score functions because we know delta, we know H's, right? We can calculate them. So once we calculate, it's going to be 0, 2, and so before we calculate, will it predict the correct class? Yes, because the argmax of H, maximum of H is 2, which is attained at the prediction Y, prediction 1. And it was actually coming from the first class, so it's going to give us the correct answer. And then looking at the table and looking at the values given here, just write the function. And the function, the loss function, your loss value will be 2. part 3 is using the same thing, parameterize, involve C, then average over n samples. And the last part is the subgradient of this. So in finding the subgradient, one issue that we have here is the maximum. Got to somehow manage around the maximum, and that is given in the hint. So how do you get rid of the maximum? Since you know that G in gradient Fk is implies G is in gradient F, so it's enough if you find a subgradient of Fk, right? And you do that by just plugging one specific y value, which is given, which line? Here, this line. So just plug this y head I to get rid of max. Once you get rid of max, you're able to write the subgradient. Since the first part doesn't depend on v, only this part depends on v, and gradient of this is just simple linear algebra. Kernelized logistic regression. Just putting everything together again in the same way given in the text. You know your functions, your hypothesis space is the linear hypothesis space, the inner product of v and cx. You need to have the square law, so you write the norm squared of v, of the parameters. And there's a regularization parameter, just put it in front of it. Then the rest is, of course, the unregularized loss, which is the average of the average over the data of the loss function. And loss function is given, L of m above. Just replace m with the, again, with what's given here, y times f of x. And f of x, f comes from the hypothesis space, so f of x is just v times pcx. So you just put everything together and write it down. Equivalent form with what? Plus here c by m, what was c? If c is constant, that's fine, but if c is a parameter, then we don't have it, right? We don't have that parameter here. But if it's constant, then that's fine. And so we want to use the representative theorem in the next part. We want to have the two forms look similar. So what we do is we take r as the square function. It takes the number x, gives x squared times some lambda. And the point is that x squared satisfies the assumptions of the representative theorem, which is the fact that it has to be strictly increasing. Now, what do we do? If we know that the assumptions of the theorem is satisfied, we can find a solution that's given, that's described in the body of the theorem. So we just write the candidate solution as the linear combinations of x's, and then plug it in the inner product. Once we plug it in the inner product, we can take the sum out because inner product is a bilinear function. In each variable, it's linear, so we can take the constants out and the sum out in the same manner. And that gives us the inner product of c's only inside, so we get rid of the, take the coefficients out. And what's that inner product? That inner product is the kernel. It's again given in the body of the problem. So so the last line is just a notational difference. So this is the kernel of XIX, and we kernelize that part. And we continue in the third part of the question. So now we want to write all the, remember the j of v was this. Now we want to write everything we see here in terms of the new notation. Now we just reformulate everything in terms of x. Is what's v squared, norm v squared. It's, we have norm of x, it's just inner product of x comma x square root. Right, you can write the norm in terms of inner product. That gives you the first term of j. And for the second term of j, what do we need? We need to write this inner product, v times c. So we plug v in that part, again taking the coefficients out. Kernelizing is in the second part. We just get the representation of the loss we want in terms of alpha, in terms of the coefficients. Right? It should be straightforward. Any questions? Okay, so the sixth problem is correlates for classification. We have the square loss y minus prediction squared, obviously, but in this probabilistic setting, you look at it given the data, so it's given x, and we take expectation after that. So one thing you should know in this problem is that so what is the thing that minimizes the square loss? Do you remember? Some of you taken the class last semester, so you might remember the fact that the expected value, so the conditional expectation minimizes the square loss, right? But I mean, you didn't need to know that for the exam, but it's at least important to somehow remind yourself. So here, what do we have? So the problem again describes itself. We have to form expected value of the square loss given x, write it out, take the derivative with respect to y hat, and solve for the parameter we want to solve, right? And y is a discrete random variable. So given x, there are two values for y. It's either 1 or minus 1. So given x, I can write it, oops. Given x, if there are two cases, y is either 1 or minus 1. If it's 1 with probability p. Then it's p times 1 minus y hat squared, which is the function inside, right? Plus, the other option is that y is minus 1. So here is y minus 1 in the second term. And that happens with probability 1 minus p. And this is the function here. So the expected value of functions of random variables is taken in the same way. Right? So here, maybe probabilistic fact we should know was how to calculate expected value of this, expected value of f of x in terms of the distribution of x. Once you find this expression, the rest is more straightforward. You want to find the arguments, you just take the derivative with respect to y hat, then set it to 0, solve for y hat. Y hat is 2p minus 1. And p here in the solution, for simplicity, was representing pi of x. So the actual solution you should have written should be f star of x is equal to 2 pi x minus 1. Then, of course, the last part is just solve pi for f. It's just a simple algebra. Second part. Show that the square loss is a margin-based loss. M margin is y head. L of m is 1 minus m squared. Then how do you move forward? The loss that you had was y minus y head squared. If you write it out, you get the terms y times y head. So you can group them in terms of y times y head. Maybe the tricky thing is, the hint here tells you that this y squared is always 1 because it's either 1 or minus 1. This part is fine, we don't have to deal with this because this is m already. I can write it in terms of m. And this y head squared, again I can write it, since y squared is 1, I can multiply y head squared with whatever I want. So y squared times y head squared is, I can add that factor to write it in terms of m. The whole point is just finding ways to extract m in the equation. Then I get 1 minus m squared. Conditional exponential distributions. You're given the family of functions we have. And we're given a map from W. Any questions? From WTX to lambda. So given x, my parameter lambda can be characterized using the parameter v as v transpose times x. Then I can just replace my, the function here, lambda times e to the minus lambda y, by what I have lambda to be when I'm given x, which is again rewriting this function here, replacing lambda with exponential w transpose times x. Second part, given data, given n many variable samples like this, they're independent, so I can write the joint distribution as the product of their individual distribution. That's the independent sampling assumption. Normally you would have to write the parameterized by v of y given x. They're vectors. But if you know that they're independent, you can just factor them out and multiply them. And in the multiplication, you replace it with the expression you found in the first part. And again, log likelihood is just taking the log, but in the log likelihood, what's important is that you can always get rid of the terms that doesn't involve your parameters. Remember in the Gaussian case, if you look at the log likelihood, you have this product of factors of 1 over square root 2 pi's. And all that doesn't matter in your log likelihood because you are not interested in the values of the log likelihood. You are interested in the location in the domain that maximizes the log likelihood, right? That's the whole point of doing maximum likelihood estimation. Taking log just makes things easier to do the differentiation. And that's another sign that the values of that logged function is not important. The location of the point in the domain is important. That's what matters for you. And that's represented in the fact that the W star that you're interested in is argmax of J of W, J of V, W, yeah, W in RD. What numerical methods did you use? You could have used any optimization would be good. So one, this describes as a stochastic gradient descent because we just take one sample from the whole sum, and then we write the derivative of that sample, and then we take a step in the negative of the gradient of that particular example, multiplied by some positive step size. It's just a description of a stochastic gradient descent. I could have used this sum. That would give me gradient descent. And that this is, you don't have to find the whole algorithm. It's just a step. Again, in the same way, it's the functional approach. Now it's some function in the exponential. Just write the j. Again, take the derivative with respect to f. It's pretty much the same way of taking derivative with respect to a variable. If you parameterize your function, then you could have used chain rule to apply the chain rule to use this formula and apply it to chain rule to find the original expression with all the parameters you have for the purpose of coding. Then in the same way, it's just argmin over the hypothesis space of your loss function, gradient of the loss function. I guess that's the end of the exam, right? There's no more pages. Oh, okay. Any other questions regarding the exam? Huh? I think there are a few typos. Once they're fixed, David might post it online. He might not post it online, but if he doesn't, then he'll put it on Piazza. So you'll have access to it, but I think it's better if exams are somehow not like publicly accessible as a class material. But I don't know, maybe the video is accessible, so maybe we already broke that part.
When do you expect we'll get it back?
In a few, I think, let me think. Hopefully next week in class, or maybe some other time when, if we don't want. Yeah, sometime next week, I believe.